The ALU is the calculator inside a processor. Its job is to perform arithmetic add, subtract, multiply, divide, and logical operations, and OR, XOR, NOT. Binary addition example. Adding two 4-bit numbers 01015 and 00113. The ALU adds each bit column from rightmost to leftmost, producing 10008. The carry out from the most significant bit becomes the carry flag C. Flag generation. After every operation, the ALU sets status bits that tell the rest of the CPU what happened. Common flags are 0Z set if the result is 0. Sign S copies the most significant bit of the result, useful for signed numbers. Overflow V indicates signed overflow. For example, adding 0111 plus 7 and 0001 plus 1 gives 1000 negative 8 and V equals 1. Carry C indicates an unsigned overflow. Logic example, 1100 and 1010 equals 1000. The ALU simply applies the logical operation bit by bit. Real-world analogy. Think of the ALU as a kitchen appliance that can blend add, chop and, or season XOR ingredients bits. The flags are the indicator lights that tell you if the bowl is empty 0 or if the blender overflowed carry. The control unit CU decides what the processor does at each micro step. It does this by issuing control signals that activate registers, the ALU, memory, etc. Micro operations are tiny actions such as load register R1 with the value on the bus, or increment the program counter. PC the CU strings these together in a fixed order defined by the instructions format. State machine design. The CU can be modeled as a finite state machine, FSM. Each state corresponds to a micro step. Transitions depend on the current opcode and sometimes on condition flags. For example, a simple FSM for a load instruction might have states fetch, decode, read memory, write register, done. Hardwired versus micro-programmed. In a hardwired CU, the FSM is built directly in combinational logic, fast but inflexible. In a micro-programmed CU, the FSM is stored as a small ROM of micro-instructions. The PC of the microcode UPC steps through them. Analogy: imagine a factory assembly line. The CU is the manager who hands out work orders, micro-operations to each worker, a LU registers, and moves the product instruction from one station to the next, using a checklist state diagram to ensure everything happens in the right order. The register file is a small fast memory block that holds the most frequently used values. Architecture typically organized as a matrix of n rows registers and W columns bit width. Read ports allow simultaneous reading of two registers, while a single write port updates one register per clock. Read/write timing reads are usually combinational. The data appears on the output after a short propagation delay, often within the same clock cycle. Writes are sequential. The new value is captured on the rising edge of the clock. This timing enables a read first, write last rule that prevents a write in the same cycle from corrupting a read of the same register. Register allocation strategies. Compilers decide which program variables live in which registers. Common strategies include linear scan fast scans live range intervals and assigns the next free register. Graph coloring builds an interference graph and colors it. Each color corresponds to a physical register. Spilling: when there are more live variables than registers, some are stored in memory spill. Analogy: think of the register file as a set of lockers in a school. Each locker register has a unique number. You can open two lockers at the same time to peek inside read ports, but you can only put a new book in one locker at the moment the bell rings write port. The school schedule compiler decides which students' books stay in lockers and which have to be left in the library memory when lockers run out. Explanation: an instruction cycle is the lifetime of a single machine instruction inside the CPU. It is usually split into fetch, decode, execute, memory, and write back stages. Timing diagram: shows the state of the clock, control signals, and data buses for each half cycle. For a two-phase clock, the first half phi1 may enable the address bus and start a memory read. The second half phi2 latches the data into the instruction register. Fetch: IR load equals 1, PC inc equals 1. Decode: ALU op equals add, parenthesis PC plus offset parenthesis. Execute mar n equals 1, parenthesis place effective address on address bus parenthesis. Memory mem read equals 1, mdr load equals 1. Write back reg write equals 1, parenthesis store mdr into destination register parenthesis. Cycle level control signals are generated by the control unit based on the current state of the finite state machine. Some designs use a micro code sequencer that outputs a one-hot vector of control lines for each cycle. Analogy picture a relay race. The baton parenthesis instruction parenthesis is passed from runner to runner parenthesis pipeline stages parenthesis. The timing diagram is the race clock, showing when each runner starts and finishes. The control signals are the referee's commands telling each runner when to run, stop, or hand over the baton. The data path is the network of functional units, ALU, registers, shifters, and the buses that move bits between them. The width of the main data bus is chosen to match the processor's word size. For a 32-bit CPU, the data bus is 32 bits, allowing one word to be transferred per cycle. If the address bus is a bits, the maximum addressable memory is 2 to their locations. Example, a 20-bit address bus gives 1 megabyte address space. To reduce pin count, many designs share the same physical lines for address and data, a multiplexed bus. In the first half cycle, the lines carry the address. In the second half cycle, they carry data. This is common in microcontrollers with limited pins. Multiplexers, or muxes, are used to select between multiple sources. For instance, the ALU's second operand may come from either a register file or an immediate field. A 2-to-1 mux controlled by ALU source selects which value to feed. Imagine a highway system where cars' bits travel on lanes buses. The lane width determines how many cars can travel side by side, which is like bus width. A reversible lane that can carry cars in one direction during the morning and the opposite direction at night is like an address data multiplexed bus. The same physical road serves two purposes at different times. Explanation: the memory interface unit, MIU, bridges the central processing unit and the memory hierarchy, caches, and main RAM. Cache memory mapping: 3 classic schemes. Direct mapped: each memory block maps to exactly one cache line. Index equals address modulo number of lines. Tag bits are stored to verify a hit. Set associative: the cache is divided into sets. Each address maps to a set, and the block can occupy any line within that set. A 4-way set associative cache with 64 lines has 16 sets. Fully associative: any block can go anywhere. A comparator checks all tags, which is expensive. Bus protocols: commonly used are SRAM or DRAM protocols with signals like REQ, ACK, R/W, OEWE in a synchronous bus. For example, DDR, data is transferred on both clock edges, doubling bandwidth. Latency computation: total memory access time equals hit time plus miss rate times miss penalty. Example: hit time is 1 nanosecond, miss rate is 5%, miss penalty is 100 nanoseconds, which gives an average latency of 6 nanoseconds. Analogy: think of the cache as a front desk clerk that keeps the most frequently requested files, documents right at the desk. When a visitor asks for a file, the clerk checks the desk first, which is a hit. If it is not there, the clerk goes to the storage room, the main memory, which takes longer, the miss penalty. The mapping scheme decides how the clerk decides where to put each file on the desk. I/O subsystems handle communication with the outside world keyboard display network. I/O register mapping. Each peripheral is assigned a range of memory-mapped addresses. Reading from or writing to those addresses actually accesses the device's internal registers. For example, a UART data register at FF10. Interrupt vectoring. When a device needs attention, it raises an interrupt line. The CPU finishes the current instruction, saves its state, and jumps to an address in the interrupt vector table. IVT: the vector contains the address of the interrupt service routine. ISR priorities may be handled by a programmable interrupt controller, PIC. DMA, direct memory access, allows a peripheral to move blocks of data to and from memory without CPU intervention. The CPU programs the DMA controller with source, destination, and length. Then the DMA takes control of the bus, reads and writes data, and finally raises an interrupt to signal completion. Analogy: imagine a restaurant kitchen CPU and a pantry memory. Small orders I/O register reads are taken directly at the counter. Larger bulk deliveries (DMA) are handled by a delivery robot that walks straight to the pantry, fetches the items and returns, letting the chef focus on cooking. Example, to send a byte over a serial port, the CPU writes the byte to the UART's TXD register, memory mapped address. The UART hardware then shifts out the bits over the wire while the CPU can continue other work. Pipelining allows several instructions to be processed at overlapping stages, much like an assembly line.
A hazard types.
Data hazard, an instruction needs a result that is not yet written back. For example, add R1, R2, R3 followed by sub R4, R1, R5. Solutions, forwarding, bypass the ALU result directly or stall, insert a bubble. Control hazard occurs after a branch. The next instructions may be wrong if the branch outcome is not known. Techniques, branch prediction, fetch stage flush. Structural hazard, two instructions try to use the same hardware unit in the same cycle, for example, two memory accesses. Resolved by adding extra resources or scheduling. Stall insertion, the control unit asserts a stall signal, preventing the program counter and pipeline registers from advancing for one or more cycles. The bubble propagates downstream, allowing the needed data to become available. Throughput formulas. For a pipeline with K stages and ideal conditions, the instruction throughput approaches one instruction per cycle, IPC equals 1. Real IPC equals 1 divided by 1 plus average stalls per instruction. Example, if on average 0.2 stalls per instruction, IPC equals 1 divided by 1.2, approximately 0.83. Analogy, think of a car wash with several bays stages. If a car needs extra soap, data hazard, the next car must wait, stall, or receive the soap from the previous bay, forwarding. The overall number of cars washed per minute depends on how often you have to wait. Example, a 5-stage RISC pipeline, instruction fetch, instruction decode, execute, memory, write back, for the code. Load word R10, R2, add R3, R1, R4. The add needs R1 early. Without forwarding, a stall is inserted after the load word, giving a total of 6 cycles for 2 instructions. IPC equals 2 divided by 6 equals 0.33. With full forwarding, only 1 stall is needed, total 5 cycles. IPC equals 2 divided by 5 equals 0.4. Explanation, performance of a processor is measured by how many useful operations it can complete over time. Key metrics. CPI, cycles per instruction, average number of clock cycles each instruction takes, computed as CPI equals the sum over I of ICI times CI divided by the sum over I of ICI, where ICI is the instruction count of type I and CI is its cycle count. MIPS, million instructions per second. MIPS equals clock frequency megahertz divided by CPI. It gives a rough speed estimate but ignores instruction mix.
Execution time.
Time equals instruction count times CPI divided by clock frequency. Example, a program with 10 to the power 6 instructions, CPI equals 1.5, clock equals 2 GHz. Time equals 10 to the power 6 times 1.5 divided by 2 times 10 to the 9 equals 0.00075 seconds, 0.75 milliseconds. Sample problem. A benchmark runs 2 times 10 to the power 6 instructions. The instruction mix is 40% ALU, C equals 1, 30% load store, C equals 2, 20% branch, C equals 3, 10% float, C equals 5. Clock equals 3 GHz.
Compute CPI.
CPI equals 0.4 times 1 plus 0.3 times 2 plus 0.2 times 3 plus 0.1 times 5 equals 0.4 plus 0.6 plus 0.6 plus 0.5 equals 2.1.
Execution time.
Time equals 2 times 10 to the power 6 times 2.1 divided by 3 times 10 to the power 9 equals 1.4 times 10 to the minus 3 seconds equals 1.4 milliseconds.
MIPS.
MIPS equals 3000 divided by 2.1, approximately 1429. This illustrates how a higher CPI, more complex instructions, can outweigh a higher clock frequency. Analogy, think of a factory that produces widgets. CPI is like the average number of minutes each widget spends at a workbench. Clock frequency is the speed of the conveyor belt. The total production time depends on both how fast the belt moves and how long each widget stays at each station.